Okay, all we're going to do today, we're going to take some notes, get back on the swing of things today, keep it pretty easy. That's what I want to do today. We're probably looking at a homework assignment tomorrow. My goal today is to talk about a couple different topics that we've definitely discussed before break, but to get back in the swing of things so that you kind of know what we're doing. So you're not like completely lost. If you haven't already, try to check out some of those videos before break. Leading up to, what the types of angles are when you have lines that are either parallel or not parallel, transversals, that type of thing. So that's where we kind of left off before break. Today, the goal is to go through how to use some of those terms, like why did I bring those up? Why did we go through them for like 3 days or so? Because we need them for what we're about to talk about, all these properties that will discuss how they're related. Okay? So again, we're moving on to section 3.2. I think we definitely did enough problems where you should get familiar with those angles. You guys did a pretty nice job in class with that. What we're moving on to, obviously, we're still sticking with parallel lines, but now what we're doing is we're going to be talking about the properties of those angles themselves. Not just what they are, but the actual properties about them. And that's what we're going to discuss today. And maybe at the end of class, I'm going to try to change your perspective on things. That's what I want to talk about, on especially this concept, this idea of parallel lines. So that's what we're going to do today. All right? So let's jump right in. Let's talk about our goals today. I want to talk about some of the vocab terms that we're going to talk about. So vocabulary reviews, things we should know about, and then there's some new ones mixed in here. Okay, obviously, do we know what a parallel line is? Okay, by definition, there's two parts to a parallel line. They're on the same plane, so they're coplanar, and they don't touch. Those are the two parts. You have to have both for it to be parallel. Okay, they have to be on the same plane, not touching. The same plane idea, the reason why they state that, is so that you don't have that idea of skew. Skew don't touch, but if they're on the same plane, the only way that they can't touch is if they're parallel. That idea. We're talking about angles. Remember, what forms an angle are two rays. Two rays, or lines that intersect, that type of thing. These are angled, these types of angles. Now, obviously, we're going to get into the properties today. So, what do we remember about the word postulate? What was that definition from chapter 1? What do you remember? It was actually chapter 2. What do you remember about postulates? In fact, what is a postulate? We've had a lot of them. We've had, what? I think up to this point, we've had 11 of them. But what does the word postulate actually mean? Something that's so inherently simple, there's no explanation needed. We accept it as truth. Sometimes the postulates can push that boundary of your comfort. Like, wow, I don't know how that works. I don't see it. We're going to discuss that today. The first one is definitely one of those cases where you see it and you're like, how does that work? I don't understand that. We're going to discuss that today. Theorems. What about a theorem? How's that different than a postulate? How are these two different? How is a theorem different than a postulate?
Theorem.
Exactly. Thank you. So, you need to prove theorems, right? You actually have to show why it works. Because it may not be easy for everyone. Maybe it's like one of those things like, still don't quite get that, but okay, I can see like your logical steps. Usually to prove theorems, we use a lot of definitions or postulates to do that. Okay? All right, so this is our kind of our goal today. We are definitely going to hit the first couple of properties about these angles we've been discussing up to this point. All right, now one of the key terms we've been talking about last week and the week before, transversal. Okay, transversal is that one particular line that crossed a bunch of others. So we're going to see that right away in our pictures. In fact, a lot of the theorems will have this as one of their main vocabularies and postulations. They'll have this as the main word, transversal. Then the types of angles we're going to look at today. Obviously, we're going to look at corresponding angles as one of the tougher type of angles we had last week. The other type we're going to talk about is alternate interior angles. That was one of the easy ones. We'll discuss that definition today as we get through it. Then the next one is same side interior, and if you notice, I put a little star next to this one. Okay, there's a couple different reasons. The book, I find this really odd. The book doesn't give this the same name. They don't, like in section 1, they called them same side interior. Then it moved on to section 2, and it changed the name all of a sudden, which I thought was really weird. I've never seen that before. Your book is the first one that I've ever seen that. So I'm putting a little star next to that, and we'll talk about what the book actually calls it, which I find funny. And then the other reason I put the star there is that it doesn't give both theorems about this one, which is weird. Like alternate interior, there's two theorems. There's like the first one, and then there's the second one, which is alternate exterior. Right? There's always a pair. There's two alternates. Well, there's two types of same sides. There's same side interior, same side exterior. The book never shows that theorem, which I think is really weird. It's odd. Even though there is a theorem there, it never talks about it. It just assumes you know it, which I think is odd. So yeah, so that's why I put a star next to it. On the actual slide, it'll also have a star, so you know which one I'm talking about. And then perpendicular. That was a word we've seen since the very first day. What do atoms that are perpendicular represent? What is that? What is a perpendicular object? What does it mean? Exactly, makes 90 degrees. With whatever object it's intersecting, right? They can be lines, rays, planes, objects. If they're perpendicular to each other, they make 90 degrees. They're right angles to each other. Well, that's one of our theorems today. We're going to talk about like a perpendicular idea. All right. Questions on the main things here we're going to discuss. Okay, now as we go through these postulates and theorems, we'll talk about these words again. We'll define what each of these words are as we go through them. Okay, let's jump right in. Are you taking off already? All right, here we go. Postulate 3.1. Okay, all right. So the first postulate here. Okay, postulate 3.1. It has its own terms, has a picture. Now again, it's a postulate, so we don't prove them. We accept them as truth. Those are one of the things we talked about. I'll give you the name. It does have a name over here. In a second, I'll give you that. Let's go through the words first. Let's look at the picture, and then we'll try to figure out if you guys can figure out what the name is called. Okay, all right. So here's the words. This is all it says. If two parallel lines are cut by transversal, so again, parallel lines don't intersect, they're on the same plane, and they're cut by transversal, that transversal is a line that crosses both of them, then each of the corresponding angles, each pair of corresponding angles, I should say, are congruent. Now, what does the word congruent mean? Equal. Size, shape, and measure. Everything is equal. Okay, so we're talking about corresponding angles. Now, I'm going to give you the picture here that has a bunch of different angles on it, and let's do that quick review and figure out which angles are corresponding. Okay, but I'm going to let you write this down first, because I know a lot of you are trying to scramble before. So. Again, the slideshow will be online later, so hopefully by this afternoon. Now again, this postulate we're going to use quite a bit. It's actually one of the main reasons why some of these theorems work, is this one. So we can't prove those theorems without this. It's going to be our fallback property we need. Alright, so let's give a picture of parallel lines. We have a bunch of angles on it. So which lines are parallel? How do you know parallel lines? What's the little symbol they use? Yeah, little purple triangles, pink triangles. I don't know what color that is to you. It looks pinkish purple to me. And then they also have, if they have like the names of these lines, let's say this is line M and N, they can use a little parallel symbol, like M is parallel to N. That means they don't touch, right? And then this line L could be our transversal. It's going through all of them. Okay, so we have a transversal, we have parallel lines, that sort of thing. Now, we have a bunch of angles here. We have 1 through 8. Let's talk about the definition of corresponding. It's one we discussed last week and I think the Friday before. Corresponding. Angles that are one's interior, one's exterior. Okay, so it's a pair, right? One's interior, one's exterior. They're on the same side of the transversal. So the transversal is L, so you either have to pick top or bottom. You have to commit to one of them. And they don't touch each other. They're non-adjacent. So now, what I mean by interior and exterior, like these 4 here are interior. They're squeezed between the parallel lines. They're inside the sandwich. These are the exterior angles. So we're picking one that's interior, one that's exterior. They're on the same side of the transversal, and they don't touch. They're non-adjacent. So can somebody give me a pair? 1 and 3. Give me another pair. 2 and 4. Another pair.
8 and 6.
And 6 and
5.
They're color coded. That's what I did. I color coded all 1 and 3. Yeah. Reds, 7 and 5 color coded, 6 and 8, and then 2 and 4. Okay, so yeah. So the color coding ones are the ones that are corresponding. Now, what this theorem or this postulate is saying is that they're equal to each other. So, like when the first pair we said was 1 and 3. These angles are actually this exact same angle. That's what this postulate is saying. Now again, we don't prove that. We accept this truth. Now, come back. Come back. Oh, there it is. All right. So we have 2 angles that are equal. Now, why we accept this as truth is this idea falls back to Algebra 1. Why parallel lines have corresponding angles that are equal is because their slopes are the same. If you go back to the definition in algebra, the slopes have to be the same. That's the tilt, right? That's how far you're rising versus running. Well, that's based on angles. When you rise so many, so let's say this is like the origin, right? When I rise so many and I run so many, it forms an angle here, if you can see that, which is based on the x-axis and up, right? And that's the same over here. If we pick this as the origin, it's the same rise and run according to algebra. Well, that forms an angle, which is the same with the x-axis. That's why the angles are actually the same. It's because their slopes are the same, and it forces the angles to work. Now, we are going to go through, like, eventually in this class, we will eventually get to the point where we can actually find what those specific angles are. Like when we have coordinates and stuff. That's one of our goals in the later chapters, to go through trig functions. You know, if I set up a triangle there, if you can actually see, I do have a triangle. There is a triangle there. There's actually a perfectly right triangle. We'll actually be able to figure out angles of this when I have coordinates and all that good stuff. So that's something we're going to look at eventually. But the idea here is that these pairs of corresponding are automatically equal because their slopes are the same. Now, we'll eventually come back to this idea of parallel, but does everyone understand this concept of corresponding? The angles are exactly the same number. Okay. So, if I told you angle 1 is 60, that's 60 degrees. What would angle 3 be? 60. And then that 60 can transfer through using vertical. And same thing, 5 and 7 are both 60s because they're corresponding. And this is whatever's left over. Now, if this is 60, this has to be 120. That has to be 120, even though it's drawn terrible. I should have the other angle. But you guys get the idea, right? I can figure out angles. Okay, we're going to use this today. This postulate is the reason why all the rest of the theorems work. And I'll discuss that as we go through. This is actually the main reason why these other theorems work. Okay. So that's the title of this thing. What do you think it's called? What do you think this postulate is called? The name of it is. Don't think too hard about it. Brian, what do you got?
Alternate.
Nope. What type of angles are they using? Hey, that's an thing. Corresponding angle postulate. They didn't get real creative with the name. corresponding angle postulate. I don't care if you know the number. I don't really think about like postulate 3, 1 or anything. I just remember it's the corresponding angle postulate. Corresponding angles are equal. Okay. Questions, comments, concerns on the first one? Easy. All right, let's move on. Theorem 3.1. This one does have a name as well. Actually, all the theorems we talk about today and postulates have names. We'll get back to the name here in a minute. I'll put it up here a little bit later. Let's get to the words. So it is a theorem. We do have to prove this one. So just remember that. So theorem 3.1, here's the words. We have two parallel lines are cut by transversal. If you notice, it's the same wording as the last postulate. Then each pair of alternate interior angles are congruent. Alternate interior. We're going to prove this one. It is actually really straightforward how we prove it, but I do want to walk through it. And yes, we do have a picture and all that. Two parallel lines cut by a transversal, exact same wording as the last postulate. Parallel lines, transversals going through both of them. Then we have a pair of interior, alternate interior angles, I should say, that are equal. Okay, so as you guys are kind of ready, I'm going to give you the picture. Here it is. It is a different picture than before, different numbers, different spots. Okay. So let me give the names to these lines. Let's call this line X, and let's call this line Y. And the transversal, let's call it Z. Okay, so what we're trying to show here, what we're going to try to prove, is that maybe angle number 1, that is an alternate, or that is an interior angle, right? These are all interiors. It's equal to its alternate interior angle. Now, alternate means they're on the different sides of the transversal. Transversal Z, so one's up on top, one's on bottom. They don't touch each other either. So which one's the alternate interior to number 1? 3. Color code, right? I think I heard what you said. Alright, so 1 and 3. That's what we're going to try to show. I want to show that those angles are the same. And why? Why are they equal? And it's really straightforward. Okay, so when we start the proof, because we do have to do a proof of it, okay, we have to start with what we're given. The only thing that we're given is that X is parallel to Y, and that Z is the transversal. Okay, and that's our given. Alright, so X and Y are parallel, Z is the transversal. Now, what we're trying to show in the very end, last step, 1 and 3 are equal. That's what we're going to try to show. Angle 1 and 3 are the same. Now, we're going to start with the obvious fact. One of the things. So I'm going to throw in an angle in here. I'm going to throw an extra angle. I'm going to throw angle number 5 in here. And that's going to be an exterior angle. Okay. Now, if you look at that picture, 5. Do you agree that 5 is on the exterior? It's on the outside. What we just learned in the last slide, that postulate, angle number 5 is equal or congruent to what other angle in this picture? Say it again. 1. We know that. Angle 5 is equal to angle 1. Now the reason why we know that is the corresponding angle postulate. Corresponding. One's interior, one's exterior, and then on the same side of the transversal. So it's postulate 3-1, you're going to call it. So its corresponding angles are the same. So 5 and 1 are the same. Okay? So we just proved that. Now, what else can you tell me about angle number 5? It's equal to 3. Why? What? Heard it? Vertical, yeah. So, number 3, angle 5 is most definitely congruent to angle number 3 because they are vertical to each other. They're vertical angles. We have that theorem, vertical angle theorem. I believe it's theorem, what is that? 2 point, is 2 point, is it 2.8? I think it was 2.8. I have to go back to it. I think it's 2.8. Okay, so we have vertical angles. They're actually, the funnel system is actually working. So they're straight across from each other. They're made from verticals across. So if 5 is equal to 1 and 5 is equal to 3, what can you tell me about 1 and 3? Yeah, they have to be equal because that's the transitive property of angles. That these are all equal to each other. So angle 1 is definitely congruent to angle number 3, which is the transitive property. That was one of our theorems as well. And that is what we're trying to prove. We're trying to show that 1 is equal to alternate interior is the same. Now again, those are back to chapter 2. I believe transitive property is like 2.5. Let me go back and look. Transitive property. 2.5 is the transitive property, like I said. So I was right on that one, 2.5. And vertical is, I believe it was 2.8. Yeah, 2.8 is the vertical angle. So if you like that number system, they're both around page 154. So 153, 154. All right. Questions on alternate interiors. So that means if you look at that picture, 1 and 3 are equal, and then it also means that 2 and 4 are the same. They're not equal to 1 and 3, but 2 and 4, or whatever those angles are, they're equal to each other. Okay? So I'm not saying that these angles are equal. They're obviously not. This is actually a small angle, that's a really big angle. But these are equal, and then vice versa for the other. That's ultimate here. The only reason why it works is because that corresponds. Okay, questions, comments on 3.1. Now, what do you think the name of this is called? Hey, there you go. It's alternate interior angle theorem. Real creative on the naming process. I know. Okay. Questions on this one at all? It was a theorem, we did have to show it, and the only reason why it works is because of the last postulate. Okay, let's move on. 3.2 now. 3.2. Okay, new picture again. Alright, so here's what it says. 2 parallel lines cut by transversal, same wording as always before. Then each pair of same side interior angles are supplementary. Notice it didn't say congruent. Ooh, it said supplementary. There's a big difference there. I'll let you write this one down. Now we do have, this is the one that was starred. I put a little side note, like what they actually call this one in the book, which I find really weird. Which is not what I'm going to call it from now on. I think it's silly. Bless you. Sounds like everyone's getting sick. Okay, so same set interior angles, that's what we're going to be talking about. They're supplementary to each other. Supplementary. Okay, so when we look at this, let's take a look at the actual name. This is what the book refers to it as, which I think is really goofy. They call them consecutive. Sorry, it'll be up there in a second. Okay. So consecutive interior angles. That's what the book refers to them as. Now, what that means, they're just angles that are side by side. That's what consecutive means. Like, it's one after another. You've probably seen that word a lot in Algebra 1. You will definitely see it in Algebra 2. When things are consecutive, they're back to back to back. So, consecutive interior angles. But here's the picture. So, I don't know if it's the exact same number as I did before. But we're talking about same side interior. So, obviously, I just give you a picture here with just interior angles on it. Can somebody pick which ones are the same side of the transversal? Which ones are, give me a pair of angles that are on the same side of the transversal. 1 and 2. Or 3 and 4. Right? So we're going to look at 1 and 2. Now, what this theorem is saying is that they're not equal. Okay? Get that through your mind. 1 and 2 are not the same angle. You can kind of see that. 2 is kind of small, and 1 is kind of big. What they are saying is that we're going to try to show that angle 1 and 2 have to add to make 180. And this only works if the lines are parallel, which are really goofy. So they're actually saying that they're supplementary to each other. So if I gave you angle number 2 is 30, then angle 1 would have to be 150. That's what this postulate or this theorem is saying. Now to show that it's pretty straightforward. We're actually going to use the last theorem to do it. I've actually seen this one used. I've seen this proof done 2 different ways. They can use the corresponding idea, or they can use the alternate interior idea. So I can do it 2 different ways because the proof is the exact same. There's just one slight difference. Okay, so let me give some names to these lines. Let's call this line A and B, and let's call the transversal C. All right, and I want to show this in the end. This is when I want to show that this actually does work. Okay? All right. So let's do a little proof here, and it's really short, so I'll just kind of put it right here. All right, so line 1, we start with the given. So this is our proof. So our first given is that A is parallel to B, and C is the transversal. And again, line number 1 is the given. I just start with something. Now, I'll give you guys the choice. Do you want to do it with corresponding, or you want to do it with alternate interior? Okay, alternate interior. So that's how we're going to try to show that 1 and 2 add to make 180. Okay, so alternate interior. What we just got done learning in the last slide is that angle number 1 is equal to what other angle in this picture automatically? What's the alternate interior to 1? 3. It's automatically equal to 3. And the reason why this works, it was called the alternate interior angle theorem. Alternate interior angle theorem, so 1 and 3 are the same. Now, if you look at that picture, would you agree that angle number 2 and 3 are right next to each other? They're side by side. They're forming a linear pair. You can see that. 2 and 3 form a linear pair. They make a straight line. So what we can tell right now is that angles number 2 and 3 have to add to make 180. Angles 2 plus angle 3 have to add to make 180. And the reason why, it's theorem of 213, or supplementary, or whatever you want to call it, or linear pair. I don't care what you want to call this. Now, supplementary had its own theorem. That was theorem 2.3. The 2.13 talks about if you have a straight line, they have to be supplementary to each other. So they, either way, 2 and 3 have to add to make 180. You can see that. There's a straight line. There's all 180 degrees. Well, all I need to do now is just substitute in. Instead of having 2 plus 3, I already know that 3 is equal to 1, so I can substitute that in there. And now what I'm showing here on line number 4, if I substitute 1 in there for 3, they add to make 180. And all I did was sub. I just substituted. And that's exactly what we want to show. That actually proves that they are supplementary to each other. Supplementary means they add to make 180. Pretty straightforward. So So 1 and 3 are equal, and we already know that 2 and 3 have to add to 380, so that means 1 and 2 add. So it's just kind of this weird thing where we can transfer the properties. Okay, now here's the big thing. They're not equal, 1 and 2. Okay, you need to realize that. They're not equal. They just happen to add to make 180. That is one of the hardest things to show. Now, we will definitely need this idea later for like when we get to like rectangles and squares and rhombuses. This idea that angles like that, same side interior, can add to make 180. That's a big idea. And the only reason why that works is because we have parallel lines. Okay, questions on 3-2. What do you think they call this one? Same side interior. That's, now here's the thing. This name right here is what I pulled from every other textbook I've ever used. That name right there. Your book, for some reason, calls it this, which I think is completely goofy, and I'm never going to call it that, because we've never used that word before, ever. Which I think is weird, because this is what they told you in the last section, section 3.1. That's all we did last week. Which I think is so weird. Why would they just make up some new term? It doesn't make sense. Whatever. Moving on. All right. Let's move on to Theorem 3.3. We got 2 theorems left. 3.3 and 3.4. Okay, so that was the same side interior. Now, what you also need to know, because I did put a star next to this one, because it had a weird, goofy name. But then also remember, this theorem also applies to same side exterior. So the exterior angles would be like this angle here, which I called 5 earlier, and I can call this one 6. 5 and 6 also have to be supplementary because of how this theorem works. It's the same proof, but same side exterior angles are also supplementary. So that's just something you need to realize. They don't have a theorem, which I think is really odd. Usually every theorem always has its other pair somewhere down the road. They don't do that. Whatever. Moving on, 3.3. This is the alternate exterior angles. So 2 parallel lines cut by transversal. The alternate exterior angles are congruent. Alternate exterior angles are congruent. Okay. So you guys understand the setup, right? We have parallel lines, transversal, but we're talking about alternate exterior. So let me give you the picture here. So now I have the exterior angles shown here, 5, 6, 7, 8. Which ones are alternate exteriors? 5 and 7. They're color coded. And then the other 2. 6 and 8. Remember, definition. They have to be on alternate sides of the transversal. They can be non-adjacent. They cannot touch. That's why they pick 5 and 7. For opposite sides of the transversal, exterior angles. Non-touchable. Okay, what this theorem is saying is that we're going to try to show that 5 and 7 have to be the same angle. They have to be the same angle. Now, there's a bunch of different ways to prove this. I'm just going to do it by the easiest, fastest way I know. Because I think it's just pretty straightforward. But again, let me give some names here. Let's call this E and F, and this will be G for this line. All right, so how do we start with proof? We start with the word proof. We start with line number 1. A given line, right? All right, E is parallel to F, and G is the transversal. And line number 1 is given. Okay, you good with the setup? Always kind of start. Okay, now I'm going to throw in another angle in here because I need one. This is the easiest way I'm going to do it. I'm going to throw angle number 4 in here. I'm going to put it right here. Angle number 4. Okay, I'm putting it, it's on the interior. I don't care how you start this theorem, or the proof. I'm going to start with the postulate we learned. What can you tell me about angle 5 and 4? They're equal, because they're corresponding to each other. One's interior, one's exterior, they're on the same side of the triangle, so they're not touching. So those are corresponding. So 5 and 4 are automatically equal. And that postulate was the corresponding angle postulate. Postulate 3.1. Corresponding angle. Postulates. They're equal. Remember, the goal is here to show that 5 and 7 are the same. Okay, alright, so we know that 5 and 4 are equal. Now, what can you tell me about angle number 4, though, looking at that picture? What is it equal to? What is 4 equal to? 7. A y. Vertical, right? So on line number 3, they're vertical. That was theorem 2.8, page 154. Okay, they're vertical angles. And so since 5 is equal to 4 and 4 is equal to 7, then that forces that 5 has to be equal to 7. And that's the transitive property. And that's theorem 2.5, who's the reflexive, symmetric, and transitive property of angles. So that's what we're trying to show. Alternate extrudes have to be the same. We just showed that. 5 is equal to 4, 4 is equal to 7, so that forces 5 and 7 to be the same. So that's alternate exterior, and this is what we're trying to show. Those two are equal. And then that would also force the 6 and 8 would have to be. Okay, what do you think the name of it's called? Alternate exterior. So remember, they're not getting creative here. They're just trying to get you to understand. So far, we've talked about corresponding, they're equal. We've talked about alternate interior, they're equal. Alternate exterior equal, and the only goofy one was that same side interior, those were supplementary. Now, we have to basically kind of mix all these together, all these theorems, all these postulates, and we eventually get to the next one, which is the goofy one. That is theorem 3.4. This is our last theorem today. Eventually we'll get more of these, but these are our first couple today. Alright, so here we go. So theorem 3.4, it's got a slightly different wording. It's not the exact same wording as the last ones do. I know all the last ones said 2 parallel lines cut by transversal. It's got a slightly different start. In a plane, so we have to be in a flat surface, if a line is perpendicular to one of 2 parallel lines, so a line that is perpendicular to one of 2 of the parallel ones that are shown, then it has to be perpendicular to the other line. I'll let you write that down, and I'm going to try to explain it. I'll give you the picture here. We're going to try to prove this, because it is a theorem. And it does have a name. We'll get to the name later. And this one, the name isn't, it's somewhat obvious, but there's an extra part to it. Okay, so obviously we're in a plane, we're in a flat surface. A line is perpendicular to one of 2 parallel lines. So let me give you the picture here. So we have a couple parallel lines here that you can see. That's A and B. That's my parallel lines. But transversal T, that's my transversal, is only perpendicular to A. What we're going to try to show is that it has to be perpendicular to B as well. And these are parallel. So let's start with the given. So we're going to do this proof here, and this proof is super short. Okay, line 1, the given. A is parallel to B, and T is perpendicular to A. That is our given. So look at the perpendicular symbol. It's this little perpendicular right here. That. So upside down T, It means perpendicular. Now, what does perpendicular mean for us? 90 degrees. And you can actually see that angle there. So whatever that top angle is there, whatever you want to call it, you can call this angle number 1. That angle is 90 degrees. That's what you need to realize. So line 2, angle 1 is a right angle. And that is the definition of perpendicular, which means 90 degrees. And line 3, angle 1 is equal to 90. Definition of right. Some people just jump to the chase and say it's 90. Perpendicular means right angle. Right angle means. All right, and now what can you tell me about angle 1 and angle number 2 here? Yeah, they're equal. Why? Well, if you didn't know this, like you didn't have this there, right? How do you know that 1 and 2 are the same? What postular theorem have we talked about? What type of angle circle is called? Corresponding. We already have a postulate. So on line number 4 here, angle number 1 has to be congruent to angle number 2. That's corresponding. Okay, we'll finish this up tomorrow.
Olivia Carew, Mackenzie Garr, Jenna Hampton, Andy Cueva, Taylor Boggs.
We're almost done. We have like one left. One line. So anyone hit the lights on their way? Thank you. Yeah. Switch it up a little bit.
I like it. I like the change.
Try to
Get to know some.
keep your body guessing.
It makes it. Some people are saying. There is.
I think I'm.
Oh,
Marvin's still
practice.
Who wants to try something different again?
So
I think I'm
This
just
is part
about
one.
done trying.
today we're
I've tried
gonna test
everything,
Part 1.
so I don't even know.
Not tomorrow. That'd be crazy. After a break. All the stuff.
I think before
It's just.
I get to do, I'm gonna just give it to my dad and see what he can do. If he can't do anything, then
Open the door.